Hello everyone, I'm Hansoo from KAIST. I will present my research about smartphone-based activities of daily living to detect blood alcohol concentration in a controlled environment. Binge drinking is defined as drinking pattern that brings blood alcohol concentration to 0.08% or higher. According to previous studies, approximately 50% of young adults aged 18 to 25 have consumed alcohol in the previous months, with approximately 60% of them experiencing a binge drinking episode within the same time frame. Moreover, 49.7% of the younger generation have recently consumed alcohol regularly. These frequent binge drinking behaviors of young adults have led to various unintentional physical health issues and social problems such as bodily injuries, disease, unprotected sex, productivity loss, and drunk driving. Lack of psychological maturity for impulse control in alcohol use disorder, lack of awareness of their alcohol tolerance, and increased opportunities for alcohol consumption owing to increased social activities accompanied by peer pressure. Therefore, there is a need for a tool designed for young adults that can assist in intervening against alcohol abuse through continuous monitoring of alcohol consumption anytime and anywhere. Representative traditional method measure blood alcohol concentration, which is BAC, by self-report using the Woodmark formulation, transdermal alcohol monitoring, or breathalyzer. However, existing BAC measurement methods have problems such as stigma, delay in accuracy, and user burden such as needed to carry always. Alcohol, according to NIAAA, report the symptoms of cognitive or physical functional declines via BAC of 0.03% or higher, which is a legal limit for drunk driving in previous studies. Functional assessment methods can be applied to overcome the limitations of existing BAC measurement method. Our approach to overcoming the limitations of existing BAC detection method is to utilize the representative functional assessment method. Representative functional assessment method are neurocognitive tests or activities of daily living tests. However, traditional neurocognitive test and smartphone-enabled neurocognitive test method in previous KAIST studies have limitations, such as the learning effect of repeated tests, clinicians' need for test scoring, low sensitivity tests in mild BAC, user burden by specific testing program installation and use, and harder to measure mild decline under BAC 0.06% by simple reflexive response without thinking skill. ADLs are an alternative way to overcome the neurocognitive testing method. Definition of ADLs are fundamental skills required to independently care for oneself. ADLs can measure more complex mental workload without learning effect. Instrument ADL is more sensitive than basic ADL for detecting mild functional decline. Performance-based testing is more quantitative than self-report or impairment questionnaires. However, there are several limitations of ADLs which were created in 1963. It does not reflect modern technology-based lifestyles and require a clinician which make it time-consuming and costly, and a non-quantitative and non-automatic method is used through manual logging. As with the advancement of HCI technology, people always carry and interact with smartphones. Therefore, smartphones can capture an individual's ADL quantitatively and automatically. Accordingly, this study presents a novel concept called smartphone activities of daily living, which is S-ADL for identifying BAC. Our goal is to develop S-ADL which requires more complex functional skills with mental workload than simple choice reaction tasks in prior studies to detect mild functional changes associated with varied BAC, and explore the feasibility of S-ADL for BAC detection. So, research question 1 is how can S-ADL be effectively designed to identify BAC? Research question 2 is which specific metrics demonstrate the most substantial influence on the accuracy and reliability of the BAC model. The research process overview is first S-ADL designed to solve research question 1, and experiment procedure and BAC detection modeling to solve research question 2. We defined that S-ADL is sequence of interaction behavior with smartphone apps frequently performed in everyday life by referring to the existing ADL. We developed the S-ADL by considering tasks commonly performed on smartphone apps among existing I-ADL tasks. To design primarily S-ADL, this study investigates the most frequently used smartphone apps and functions in young adults. Finally, we defined 6 specific apps as S-ADL. This is an overview of the preliminary S-ADL, which were 5 S-ADL domains with 28 S-ADL tasks. S-ADL has a unique ADL defined as a general smartphone usage ADL, which is not limited to the specific app. This study finalized the S-ADL task by designing the S-ADL task with 3 mental workload, which are high, middle, and low mental workload tasks to observe the functional decline by the human information processing model, such as perception, cognition, motor, and thinking in the SIGCHI theory. Low mental workload tasks require the simple stimuli and reflex or fine motor skills similar to CNT, and medium mental workload tasks require 1 or 2 cognitive functions. And lastly, high mental workload tasks require various complex cognitive and fine motor skills requires. This study finalized the 5 S-ADL domains and 17 S-ADL tasks among 28 S-ADL tasks determined by mental workload. After that, we designed those S-ADL task scenarios for 17 S-ADL tasks in 5 S-ADL domains. First, we create a set of S-ADL task script, an example of S-ADL task scenario, which is phone number registration and phone call tasks showed in this figure. This is an overview of app sequence trajectories for 6 S-ADL task scenarios. We designed the 57 S-ADL performance metrics. 7 task correctness scoring metrics are asking how people correctly perform the task. 8 task UI and app transition metrics are how many times the app transition. 21 task completion time is how they fast perform the tasks. Lastly, 21 typing-related metrics consist of typing speed, accuracy, and efficiency. We conducted 3 scientists, which are embed, task switching, and sustained attention to response tasks to prove the effectiveness of S-ADL for BH detection. Those tasks were measured by accuracy and mean and median response time. This study recruited 40 university students considering various demographic factors such as sex, age, and weight that can be affected by alcohol-related functional decline. And smartphone Android OS use experiments that can be affected by S-ADL performance. This study also selected the participants with screening by pre-survey such as ODK and GHQ-12. The criteria are not addicted to alcohol, have proficient experience in using Android OS smartphone, no problem with a mental disorder and health condition. This study calculated the amount of alcohol consumed for each pH level using a Widmark formula and measured the 3 pH levels with the breathalyzer. In each pH level, participants conducted the S-ADL task using Android Galaxy smartphone and the CNT using a laptop as the laboratory experiment. As reminding the research question 2, which is specific S-ADL based metrics demonstrate the most substantial influence on the accuracy and reliability of the BH detection model. Research question 2.A, which BH detection model's performance is better among S-ADL versus CNT. Research question 2.B, what are the key performance metrics of S-ADL based BH detection model? Research question 2.C, what is the most effective S-ADL task when used to separate an individual S-ADL task? Research question 2.D, whether demographic factors and smartphone OS use experience influenced the model. The result of the performance comparison of S-ADL and CNT, the S-ADL based model showed better performance than CNT based model. And the S-ADL based best model also showed better performance than both the S-ADL and CNT based model. We identified the ranking importance of S-ADL based performance metrics using Shapley value within the top 20 features in the best S-ADL based BH detection model. Most key metrics in best binary and multi-class model, which is 81% accuracy, was typing metrics and task completion time of high mental workload S-ADL tasks such as information search and share, and SMS receive and reply, and finance management task. These results show that more higher mental workload required S-ADL tasks are important to detect BAC. We compared the performance of each S-ADL task. Tasks requiring high mental workload showed better performance than other moderate and medium mental workload tasks. All results prove the study's hypothesis and demonstrate that possible within a short time such as 30-second BAC measurement using just a single or two S-ADL tasks. We examined the impact of demographic features such as age, sex, and weight, and smartphone OS use experiments such as Android OS use years and the type of OS currently in use. The overall impact on the performance of the S-ADL-based BAC detection model was minimal, although the demographic information and smartphone use experience features led to some performance improvements in models. We discussed privacy issues and potential risks of S-ADL. S-ADL does not require personally identifiable information, which reduces the risk of privacy concerns. Nonetheless, users have a few privacy concerns when collecting S-ADL performance metrics data in external cloud servers. Possible strategies are on-device running, encrypted categorical data using a one-way hash function to prevent potential data leakage. We interviewed the user experiments of S-ADL. First interview is how did the S-ADL compare in terms of UX to traditional BAC measurement method. Participants preferred the S-ADL to traditional methods such as breathalyzer neurocognitive test because S-ADL can detect BAC automatically with more reliability and accuracy result. Do not need other device or no programs with short-time measure. Second interview is what are the problems if individual trust these ML system with over-reliance. They may overlook potential risks such as false positives and negatives. Participants has a little concern about false negative detection. They preferred S-ADL to raise awareness of drinking by quantitative indicator rather than subjective judgment, and want to only know the margin of BAC error range by naughty alarms and database. There are four discussions of this study. The first discussion question is, can S-ADL be generalizable across different demographic data, apps, devices, and platform users? Future work plans to involve a more diverse group of participants and use generalized key metrics applicable across other apps and OS because key metrics can be extracted from most apps and operating systems. Second discussion question is how can we reduce the noise when applying S-ADL in real world? To better identify S-ADL in real life, we can consider the environmental and physical context. The third discussion question is how can we extend S-ADL to include ADLs that can be captured with smartphones? We can extend the S-ADL such as shopping, smart home ADL, and driving ADL, using physical activity sensors such as motion infrared and context sensors such as GPS or Wi-Fi in the future work. The fourth discussion question is can the S-ADL approach be able to other mental health problems? Beyond the alcohol detection, we can apply the S-ADL-based functional health monitoring to evaluate the health risks to young adults associated with substance use disorders and mental health problems in further study. So, our key takeaway message is S-ADL can detect BAC with high performance, which is 81% accuracy and AUC and ROC. S-ADL performance metrics are better at detecting BAC compared to traditional performance metrics based on functional assessment without learning effect. Most key metrics have potential feasibility for applying real life, which is in the other apps and operating system. Tasks with higher mental workload can detect BAC better than other minimum and low mental workload tasks. While applying ML in HCI, S-ADL systems should carefully consider user experience and psychological impact. Thank you for listening to my presentation.